This is the first lecture from Chapter 15 about chemical equilibrium. And the first thing to understand is the definition for chemical equilibrium. It is defined as when the rate of the forward reaction equals the rate of the reverse reaction. Equilibrium has nothing to do with the relative concentrations of reactant and product, which is a very common misconception. To walk you through a bit more slowly, let's imagine we have this generic chemical reaction. When I talk about the reverse reaction, what I mean is taking whatever is written on the product side and imagine it is the reactants going to form what used to be the reactants. So an easier way to put it is the reverse reaction of this first equation is simply this. So that's important to understand because in order to have equilibrium, the chemical reaction must be reversible. Okay? And so that's the first requirement. In the beginning, when a reaction first starts, most of the time, there's only reactant present. So if we look at the first reaction, there would only be A and B present. Then over time, as the forward reaction goes, you're going to start building up some concentration of C and D. If it's a reversible reaction, then C and D will begin to collide and react with each other to reform A and B. And so you're going to get this back and forth situation. And when the forward and reverse reactions are the same rate, the system has reached equilibrium. There are a couple of graphical representations of equilibrium, which you should get familiar with. The first one is a plot of concentration versus time. Now notice that B would represent the product because concentration of the product at time 0 is 0, right? You have no product to begin with typically. And the concentration of the reactant is quite high in the beginning. Over time, of course, the concentration of reactant decreases, and over time, the concentration of the product increases. At some point, the concentrations of the product and reactant remain constant. Now, they are not equal. I'm not saying anything about what the actual amounts are. I'm just saying concentrations of reactants and products stop changing. They remain constant. That's represented by this flat line area. At that point, that signals equilibrium. Another common graph is rather than looking at what's happening to concentration, we look at the rates. And so, of course, we've seen before the rate of the forward reaction will begin to slow down as we deplete our reactant A. The rate of the reverse reaction starts at 0 because there's no product, but it picks up, and then remember equilibrium is defined as the point at which the rate of the forward and reverse are equal. So get familiar with these two types of graph. At equilibrium, even though the reaction appears to have been stopped, so if you were monitoring, let's say, the concentration of products or reactants, again, at equilibrium, there would be no change, and so you might think, okay, it stopped. It never stops, which is why the expression dynamic equilibrium is used. So the forward and reverse reaction are occurring, okay, back and forth, they're dynamic, but because the net concentrations of the reactant product are changing, it appears to the scientists that there's no change. And just a quick reminder, so you're used to seeing this single arrow for just a standard chemical reaction. When we talk about equilibrium, you'll often see this double arrow, and that simply means that you have a reversible reaction. This is not to be confused with a single arrow with double heads, okay? That's used for resonance structures. So here's the proper symbol for equilibrium. I've emphasized throughout this brief lecture that equilibrium has really nothing to do with the concentration of reactants and products. They might just freaky coincidental be equal, but most of the time the amount of product is not equal to the amount of reactant at equilibrium. But what we can say about the concentrations of reactants and product is that they stop changing, okay? So at equilibrium, the concentrations of product and reactant remain constant. Since the concentration of reactant product remain constant, it's also the case that if we took a ratio of the reactant or of the products and reactants, that would also remain constant, right? If neither one of these is changing, the ratio at equilibrium, the ratio should remain constant. And so that's kind of a lead into what we call the equilibrium constant. So if you have, again, a typical reaction that is reversible, as we can see by the two arrows, the equilibrium constant, which is designated with a capital K. Be very careful. Rate constant was a lowercase k. Okay, equilibrium is a capital K. So the equilibrium constant is defined as the concentration of the products, let's see, C and D are products, raised to the power of whatever, this should be D, raised to the power of whatever their coefficients are. Now this is where I want you to write a note to yourself and highlight it. When you are writing rate laws, okay, and you have concentrations, the exponent for the concentrations in a rate law have to be determined experimentally. You can't get it from the balanced reaction. In equilibrium, you do. You always take the coefficients and they become the exponents. So again, the equilibrium constant is products over reactants raised to whatever the coefficient of each substance is. KEQ, it's a constant. So for a particular reaction, it's a set value at a specific temperature. I will say over and over here, the only thing that will change KEQ, equilibrium constant, is temperature. So let's look at a couple of equilibrium constant expressions. Here's a decomposition reaction, and so the equilibrium constant would be products, nitrogen dioxide, raised to the power of the coefficient, raised to the fourth power. Pay attention that these different concentrations are multiplied by each other. Every now and then I get students that want to put addition signs in. They're multiplied. The other product is oxygen. It's assumed to have a coefficient of 1, so the coefficient, or the exponent, is assumed to be 1. Reactants go on the bottom. So N2O5 is a reactant. It has a coefficient of 2, which becomes an exponent. And this is the equilibrium constant. So I'm kind of beating a dead horse here, but just reminding you again that even though I'm telling you to use coefficients in the balanced chemical equation for your exponents in the equilibrium expression, you did not do that for the rate law. So don't get those two mixed up, please. So there are a couple of exceptions when you're writing an equilibrium expression. There are certain things that are left out. If you have a pure solid, which is designated with an S, okay, or a pure liquid, they are left out of the rate constant expression, okay? And that is because the concentration of pure solids and pure liquids don't change, okay? It's only solutions or gases that can change concentration or pressure. So this is no surprise if we look at this reaction and write the equilibrium constant expression. There's really no surprise here, but what I do want you to do is pay attention to the equilibrium expression at the bottom of the page. Now, if it sunk in what I just said, you should be able to tell that the equilibrium constant expression K is simply equal to the concentration of carbon dioxide gas. So what happened to the concentration of calcium oxide and the concentration of calcium carbonate? Notice calcium carbonate and calcium oxide are both solids, as designated by this S. Those concentrations don't change, so they are not part of the equilibrium expression. So in general, let's think about what an equilibrium constant K tells us. Remember that it's concentration of products multiplied by each other on the top and reactants on the bottom. So what does it mean if we have a large K? If we have a K that's greater than 1? That means that products dominate, and the language that chemists like to use is that reaction favors products. So if products dominate, they're going to be in the numerator, and you're going to have a K value that's greater than 1. Likewise, if K is less than 1, or a small number, that means the denominator is larger than the numerator, which would mean that reactants dominate, or the reaction favors reactants. KEQ is unitless. We could assign units, but it wouldn't make a lot of sense because we don't know what the exponent values could be. They could be crazy. You can have 3, 4, 5, 10 as an exponent. So we just say that KEQ is unitless. We leave them out. There are a couple of mathematical relationships between chemical equations and K values. There's like 1 or 2 slides I'm going to show on this, and that's it. I won't mention it again. But it will show up on your test. I would put these in note cards or highlight them or something so you can go back and review them. So let's say that you have a chemical reaction shown here that I just circled, and that you suddenly decide you want to reverse that chemical reaction. What happens to the K? Well, if you have a particular K and you flip the reaction so that products are reactants and reactants are product, you have a new K. And that new K equals 1 over whatever the original K was. So here's a relationship you need to do. If you reverse a reaction, the new K value is 1 over the original K value. Here's another manipulation you can do to a chemical reaction that will affect the equilibrium constant. So again, here's a generic reaction. Let's say, for whatever reason, that you multiply the reaction equation by some integer. In this case, we've multiplied it by 2. What happens to the K value? Well, you take the original K value and you raise it to an exponent equal to whatever you multiplied by. So as you can see, the original expression for KEQ is concentration of C divided by concentration A times B. If we multiply that equation by 2, we now take the original expression for KEQ and square it. So this exponent is whatever factor you multiplied the equation by. So that's 2 kind of mathematical manipulations of K. There is a third one. And the third one is, this is kind of a weird one, this would happen in Hess's law, for example, if you remember that in thermodynamics. If you add 2 reactions together, and each of the reactions, when they were separate, before they were added together, have an equilibrium constant expression. And if you combine those reactions, so let's just look a minute down here. If you have A goes to B, and you add to that the reaction B goes to C, if you add that together, your B's are going to cancel out and you're going to end up with this. So here's the new chemical equation, and what you have done for the new equilibrium constant expression is you have to multiply the equilibrium constant for each of the individual reactions that you've added. So it's kind of weird. It's almost like you do a simple math operation, the chemical equation, and end up having to do a multiplication or exponential operation on the K value. So go over those three mathematical manipulations and make sure you know them. So here's some practice. I would recommend turning the video off, and because these are not hard, you just have to remember the relationships I told you. And there are 2 questions here. See how you do with them, and then I will show you how to work them out on the next slide. The first thing you have to do is compare the original chemical equation to the one that has been changed and decide what has happened. In this first case, you have reversed the reaction. So if you remember the relationship, when you reverse the reaction, it's 1 over the original K value. So 1 over 4.63 times 10 to the minus 3, which was the original K value. So the new K of the reversed reaction is 2.16 times 10 squared. Part B, let's look at what we've done. All right, so we have reversed this reaction, and we've done something else to it. We've multiplied by 1/2, a factor, or you can say we divided by 2, however, but since we've been talking in terms of multiplication so far, we'll keep it that. So we need to do 2 manipulations to the K value. By reversing it, remember it's 1 over the original K, and whatever we multiply it by, in this case 1/2, becomes an exponent. So the new K is 1 over the original K raised to the 1/2 power, which is the same thing as square root of 1 over K. Alrighty, you'll learn in the next 3 chapters, there are a whole bunch of different equilibrium constant values, all with slightly different definitions. But right now, there is an equilibrium constant, which we refer to as K sub P, where P stands for pressure. And that is if you have any chemical reaction that has gases, because only gases can be expressed in terms of pressure, you can write the equilibrium constant instead of concentration values, you can write it in terms of pressure values. Again, the pressure values are only for the gases. So if you're asked to write a K sub P for reaction and it has, let's say, 2 gas reactants and 2 liquid products, you can only include the substances that are gases in a Kp expression. There is a mathematical relationship between Kp and Kc. Kc is simply equilibrium constant in terms of concentrations. It's the most kind of basic form. And that relationship is as follows. So capital R, as always, is the universal gas constant. And since we are talking in terms of pressure, it's the value that's liters, atmosphere, moles, Kelvin, 0.0821. T is temperature, okay, in Kelvin, of course, and delta N is what might trick you up a little. Delta N is the difference in the number of moles of product that are gas minus the number of moles of reactant that are gases. So the difference in those two is delta N. That becomes an exponent. So let's look at a basic problem. So let me rewrite the expression. Kp equals Kc and RT raised to the delta N. So go ahead and try that if you think you can, but if you can't, it's okay. I'll kind of walk you through. You're given Kc, and you know the value for the universal gas constant. Temperature is, they're actually nice. They gave it to you in Kelvin, so just plug it in. So the key here is to figure out what delta N is. So remember that's the moles of product that are gas minus the moles of reactant that are gas. So how many product molecules do we have that are gas? We have 2. That's going to be 2 minus. How many reactant moles or molecules are gas? Well, let's see. Here's 2. And then plus we have 1 more gas. So we have a total of 3 on the reactant side. So our delta N value is minus 1. All right, so when you plug all of that in, here's the Kc value. Here's R times temperature in Kelvin raised to the minus 1 power. You get that Kp is 8.7 times 10 to the 4th. And Kc was here. So there's, the values can be vastly different. Now, one of the things I want you to look at that's actually important, can save you a lot of time on a quiz or test, is there are some cases when Kp will equal Kc. They'll be the same. So look at that equation. Can you tell me under what circumstances they would be equal to each other? They're equal to each other if the delta N is 0. Anything raised to the 0 power is 1, right? So if that's a 1, Kp equals Kc. So what does it mean if delta N equals 0? That means the number of gas molecules on both sides of the equation are equal to one another. So it would mean if I had 2 gas molecules on the product side, I would need to have only 2, or exactly 2 on the reactant side. Now here's one for you to try. So go ahead and give this a shot. Calculate Kp just like we just did. Be careful of units, and I will go over it on the next slide. All right, so writing our formula again and just plugging in. You do have to remember or be sure that your temperature is in Kelvin, so you may have to add 273 if it's given in Celsius. And so probably what you need to be careful is to make sure you got delta N correct. So the number of gas molecules or moles on the product side is 1 plus 1 more. Okay, so there are 2 on the product side. How many gas molecules or moles on the reactant side? Just 1. So delta N equals 1. All right, so Kp value for this reaction is 229 compared to 4 for the Kc value. And one final reminder as I sign off this first Introduction to Equilibrium lecture. Remember, when you're writing equilibrium expressions, do not include any reactants or products that are pure solid or have a S next to them, or pure liquid. Leave those, just simply totally leave them out of your expression. So here's a good example. Okay. Water is a pure liquid. It gets left out of the equilibrium expression, and the rest of them remain. Aqueous just means something dissolved, so those get included. That's it for the Introduction to Equilibrium.